So now we're going to discuss what to do when you want to use F equals ma for a fluid element, not along the streamline like we did to derive the Bernoulli equation, but in the direction normal to the streamline. So now we're going to discuss what to do with that case. So recall that we had, in general, F equals ma gave this equation here, where basically this is just the time rate change of momentum. This here is the weight, and these here are the net pressure forces pushing on the sides of our little fluid element. And to derive Bernoulli equation, we basically just examined the terms in the streamwise direction, and by streamwise I mean in the direction along the streamline, or tangential to the streamline, however you want to call it. Now, one limitation of the Bernoulli equation is that you cannot use the Bernoulli equation to jump across different streamlines. So if we had two streamlines here, you cannot use Bernoulli equation to link a point here to a point here on different streamlines. The Bernoulli equation can only be used to link two different points that are on the same streamline. Okay, so but how do we jump across streamlines? Well, we have a general equation here, and notice that there are terms that involve F equals ma in the normal direction for this fluid element. So why don't we examine those and then see what those tell us? Okay, so in the n hat direction, we had, and if I just grab those terms, we have this centripetal acceleration term here, we have this weight term, and we have a pressure gradient term. Okay, and so this in the same way we can actually work with g cosine theta and relate that to a change in the elevation, just like we did for the Bernoulli equation here by just looking at the triangle. It turns out this is just dz dn because we have gravity acting straight down, and we'll define z as the change of elevation. We have dn and ds. Okay, so and so cosine theta by definition is just dz dn, and here the pressure is only a function of n, so I can actually take out the partials because we're not going along the streamline, we are going normal to it. So I can change that to just a differential equation instead of a partial differential equation. And we have the centripetal acceleration is equal to the hydrostatic pressure. This here is just basically rho gh, or the hydrostatic pressure, minus the net pressure forces pushing on the top and the bottom of the fluid element. Okay, so what am I going to cover here? And so we work with this, and we have that and I just basically multiply both sides by dn. So we have basically rho v squared over r times dn is equal to minus rho g dz minus dp. And recall that this r is the radius of curvature. And here, one complication is that the radius of curvature changes with the n hat direction. So say if we are starting at this point here on this streamline here, and we are going in the normal direction, because right now this equation says we can only go in the normal direction. We cannot go along the streamlines, we can only go across them. So we're going to start and we're going to go out. But notice that the radius of curvature here is smaller than the radius of curvature here. So in other words, this radius of curvature changes as we move in the normal direction to the streamline, to the streamline. So that does add a little bit of a complication, but nonetheless, we can still work with this. So here I just took these terms and then moved them to the left-hand side to get an expression equal to 0. Unfortunately, we can't. There are no games that the Bernoulli equation worked out very nice because we could get everything into a perfect derivative. Here we cannot, mainly because this r is a function of n, and we don't know what that function is. You need to define that based on your flow. Okay, but again, we just integrate this, and I'm going to integrate it between some point 1, n1, and some point n2. Okay, so essentially what this says is we just integrate this. We have a perfect derivative for p, so the integral of that's just p. We have, if rho g is constant, we have a perfect derivative for this term here. And this term here we actually have to integrate, but if we assume rho and g are constant, we can pull out the density and just integrate this between two different points across streamlines. And the velocity on the streamlines can also change as a function of the direction normal to the streamline. Okay, and so we just integrated this between n1 and n2 for the entire equation, and so this is just equal to some constant. Okay, and so here you actually have to do an integral every time. And this is valid across streamlines for incompressible, and that means rho equals constant. Flow, inviscid flow, steady flow, and this works across streamlines. You cannot use this along streamlines. For that, you can use the Bernoulli equation as long as you satisfy these three assumptions here. Okay? So, and this equation is not nearly as useful as the Bernoulli equation, so we're not going to work with it that much, maybe do a few problems. But I will do an example. And I will say that this term here is really the centripetal acceleration. And so if the gravity is equal to 0, we have, from our master equation here, we have that rho vs squared over r equals minus dp dn. I'm going to multiply both sides by dn, and then I have dp is equal to minus rho v squared over r times dn. And where I got this was I just worked with this master equation here, crossed out this term over here, and then just rearranged everything and basically solved for dp. Okay? And so what this means is that we can actually learn a lot from this little expression here, and you can conclude that the pressure is higher on the outside of circular streamlines. Okay, and so you can look at a picture here. This here is called a vortex, and we have a bunch of concentric streamlines like this and like this. What this equation tells us is that basically as we go, as we move out, the pressure will basically increase as we move out, like this. Okay, and so at the center of a bunch of circular streamlines, which is called a vortex, you can have very low pressure, and that pressure increases as we move out. Okay, and so, and you see this in weather systems. The eye of a hurricane is the center of a big vortex, and same thing with a tornado. And so there is low pressure at the center of a tornado, and that's why they can kind of lift things up and sort of pick them off the ground and lift them up. It's because you have a region of very low pressure that can sort of suck up dirt and cows and things like that. Okay, or the eye of the hurricane has a region of low pressure. So if you think about it, if you have a hurricane over here, this is a hurricane and it's spinning, and there's a region of low pressure here and high pressure outside. And if we look at the surface level of the water, here you have atmospheric pressure outside, but over here you'll have basically low pressure, and that will basically pull up on the surface of the ocean. So you have this what's called storm surge, and that is a region where the elevation of the water is actually higher than basically where it is higher than normal sea level, just due to the fact that at the center of the hurricane you have a low pressure that is basically trying to suck it up, that is trying to lift up on the surface relative to the surrounding seawater. Okay, and so these sort of vortexes and this centripetal acceleration term can cause a lot of large-scale phenomena that we have to deal with here in Florida, or growing up in North Dakota to deal with tornadoes. Okay, so now we'll give an example. So we have a flow with circular streamlines. Okay, and we define those streamlines by basically Vs is equal to some constant divided by R. Okay, and so here I just have a picture of that function, and so we have our circular streamlines, and I just plotting Vs as a function of R. Okay, and that looks something like this. Okay, and so we are to find the pressure as a function of R if P equals some P naught at some R naught. Okay, and so now we are just asked to find, basically, to add a plot here to basically figure out what is the pressure going to be as a function of R. Okay, so where do we begin? Well, we have circular streamlines, and R is the normal direction, so we need to use F equals ma across streamlines. Okay, so we need to assume, so in order to do that, we need to assume that the flow is steady, and we need to assume that viscous effects are negligible, and we need to assume that gravity is negligible. And also we are going across streamlines, so F equals ma across streamlines is valid. So going across streamlines, so F equals ma across is valid. Okay, so now for the solution. So we are trying to find P across streamlines, so we can use our relation that we derived earlier. So we have P plus rho gz plus rho, the integral from some point 1 to some point 2 of Vs squared over R dn is equal to some constant. Okay, well, by this assumption here, we are neglecting gravity. Like, this could be a hurricane, and we don't really, and that's not that big of an effect, so we can cross out that term, neglect. And again, in your guys' homework, I expect you to show your master equation like this, and then cross out terms based on your assumptions. You do not cross out a term if it is not explicitly zero or stated in your assumptions. Okay, so we need to relate, and now one thing we need to do is, this here is n, and n is the direction of the streamline, so we need to relate dn to R. Okay, and we can sort of see that by just draw two streamlines here. Again, the n hat direction is defined to point towards the center of the circle. But if you think about it, we have a radius R, and I'll have an n hat here and an n hat here. And you have R going out in that direction there. So we have that basically n hat and R basically point in the exact opposite direction. So we can conclude that dn equals minus dr. Okay? And the reason we have to do that is because we know Vs as a function of R and not n. Okay, so we can change, we can make a change of variables. And we have that P plus rho times the integral of Vs squared over R times minus dr, because that's just dn, is equal to some constant. Okay. Then we know that Vs equals some constant over R, so I can substitute that in. Then we have P plus rho times the integral of c squared over R cubed. All I did was I just took the expression for basically Vs and substituted it into there. Dr is equal to a constant. Okay. So I can integrate this, and I find if I integrate this, if I integrate this term here, I get that P equals, or not P equals, P plus rho over 2 times c squared over R squared is equal to a constant. Okay, so now we need to find that constant. So we are told that P naught, or that P equals P naught at R equals some R naught. Okay, because notice we can't take R going to exactly 0 because it becomes singular there, so we can't do that. But we know that pressure. We know the pressure at one point. So we can find this constant using that one point. So at R equals R naught, P equals P naught, and we substitute those two in and solve for our unknown constant. So we have P naught plus rho over 2, we're assuming rho is constant, times c squared divided by R naught squared is equal to our constant. So now we know our constant is just this, is just that expression there. So now we know that, and we can substitute this and put that into here for our main expression. So finally, we have that P plus rho c squared over 2R squared equals P naught plus rho over 2 times c squared over R naught squared, or doing some light rearranging, we have that P equals P naught plus c squared over 2 times 1 over R naught squared minus 1 over R squared. Okay. So that is our final expression. And just to draw what it would look like, this would be R, and this would be point R naught, and this would be P naught. And so what we find is that the pressure will look something like this. Okay. And so this is our P of R. Okay? And so you can see if you evaluate this expression, the pressure pressure is lower as you decrease R, and in fact it becomes singular and will actually become very negative and very unphysical real fast. And so, and that has to do with our description of the description of the flow by basically telling you that the fluid velocity is C over R. So the velocity itself is approaching infinity as we as R goes to 0. So clearly, this flow is not accurate, very close to the center of the vortex. In general, there's something called a Rankine vortex where that's a more accurate approximation. But we're not going to go over those in this class. And so, but in other words, you can use F equals ma to basically jump across streamlines. Okay, and you wind up with results like this. Okay,